Hey, what's up, guys? Okay, in this video, I want to talk about this so-called corners theorem. Okay, and so this is a simple application as the triangle removal lemma. So if you haven't seen my previous video about the Ross theorem and the triangle removal lemma, then you can go to check out it. Okay, so corners theorem is some combinatorics results, and it's also non-trivial and hard to see why, because it's proved by triangles removal lemma. So it's some very deep, I think it's very deep results. Okay, theory. So A is let's say a subset of n by n grid. So this is just n times n. So this is basically a tuple. X and Y, where X belongs to 1 to n, and also Y belongs to either 1 to n. Also, you take a subset of this grid. Okay, so it's A. If A is corner free, so I will explain what corner means. If A is corner free, then the size of A must be little o n squared. Okay, so let me just say what's corner. So a corner is a corner of A is the tuple. Is the three coordinates. Is a corner of A is a set. It's a set. It's hard to say. A corner of A is a set. So a corner of A is contains three points. Let's say x and y and x plus dy and x y plus d for some d non-zero, and they are all in A. Okay, so this is the corner. So what corner means that if you have x and y, and then you have x plus d y, and then you have x y plus d, and then these are d, these are d, these are set. The set of 3 points forms a corner. So this is a corner. 3 points in A, they are a corner. Okay. So this theorem tells that if A is corner free, that means that A should not be a lot of points, right? So but A is corner free. Okay, then A must be order n squared. Okay. And another way to say this is that you can define, say, Rn to be the max of, to consider all the size of A, and such that A is a subset of n squared. A is corner free. Then Rn divided by n squared must go to 0 as n go to infinity. Okay, so this is R. Okay, so let me just describe the following. Okay, so the idea is, so this theorem, this amazing thing just tell you that A cannot be constant. The density of A must go to 0. Okay, so there should not be a constant. There will not have possible positive density subset which is corner free. Okay, and the proof just basically using the following fact that come from triangle removal lemma. So let me just explain here. So remember that there's a theorem says that if you take a graph G, and if this graph G, if each edge of graph G corresponding to exactly one triangle, so correspond to exactly one triangle, then the number of the edges must be little o of the number of vertices squared. Okay, so I think it's very clear. If each edge of G corresponding to exactly one triangle, then the number of edges must be little o vertices squared. Okay, so now we can prove corner theorem. So we can do this create a graph. Right? We need to change combinatorics in the graph theory. So we let's say we start with some tripartite graph G. So this G contains the multiple three part X, Y, and Z part. Okay, so X is let's call it X1, X2 up to Xn. Okay, capital N. and xi corresponding to a line. So x is a vertices, right? X is a vertex, so disjoint union. Okay. So this is x, this is y, and this is z. Okay, so these are our graph G. Okay, so xi basically means that the line of x equals to I. So it's a line x equals to I. And obviously y is basically y1 up to yn, and the yi is the y equals to I. And then we define z to be z1 up to z2n, and the zk means a line which is x plus y equals to k. Okay, so let me just draw a picture. So this is x. This is two coordinate plane. It's a plane, right? And this is n. And this is n. And this is line called x1. This line is x2, x3, x4, and y1, y2, y3. Now this is z, right? So this is z1, z2, z3, z1, z2, z3, z4. Okay. So this is the vertices, right? So we have n line here, and line here, and two n line here. Okay, so and we need to define edge, right? Okay, so what's the edge? So we can create we can define if x and y connected. So we need to define what's the case that x and y connected, right? So this is very simple. So our definition goes as follows, right? So this is x, this is y, and they will always interact at some point, right? So they will intersect them. Okay, so let me just write down. So if x and y are connected, there's a small x in x, and the y in y is connected. If this x and y belongs to A. Okay, hopefully it's clear. If there's a intersection belongs to A, then we say then x and y, these 2 points that are connected. Okay, and similarly, if x and z connected, basically means that their intersection belongs to A. And also for y, z are connected, basically their intersection. Okay, yeah. Okay, so now it's very weird. Okay, so it's clear that what's the edges. Okay, but what's the meaning of triangle? Right? If we have x and y and z, there is a triangle here. Then it's very obvious that this triangle corresponds to corner. Okay. This is simple, right? Because you have some x and y, and then some z, and they're all in A, right? So this point in A, and then this point in A, and then this point in A, and then this must be DD. Okay, so if this 3 point in A, then A must have some corner, right? So then A has corner. Unless D is 0, right? Unless D is here. So this means something, right? So this means the following. This means that A has corner 3. Implies that each edges of G has exactly 1 triangle for each, right? Corresponding 1, because each edges can only intersect trivial. Okay, so the number of edges must be capital O V squared. Okay, and what's the number of edges? No, okay. So what's the number of edges? Number of edges is just the size of A. Okay, so size of A must be capital O squared. Okay, so that's it. Okay, but the number of size V is basically the order of A. Okay, so this proves the corner theorem. So this is one weird application of the triangle removal. Okay, so see you guys next week.